Hello guys, welcome back to my channel, and today we'll be again calculating the value of the Gaussian integral, but this time we'll be using the beta function and the gamma function. So let's get to it. So the problem, as always, is, let's call it G, is the Gaussian integral, which is the integral from 0 to infinity of e raised to negative x squared dx. So this time let's use u substitution. So let u equals x squared, such that we have du equals 2x dx. So dx is du over 2x, but x is just square root of u, so 2 times the square root of u. So our Gaussian integral now becomes, so now notice, as x tends to 0, x squared goes to 0, so u is 0, and as x tends to infinity, x squared goes to infinity, so u is also infinity, of e raised to negative u this time, and instead of dx we have a du divided by 2 root u. So let's remember this other alternate form of the Gaussian integral, because this will be helpful for us in the long run. So as the title of the video suggests, I'll be first going to use the beta function. So what's the beta function exactly? So the beta function of this takes in two arguments, a comma b, is equal to the integral from 0 to 1 of t raised to the a minus 1 power times 1 minus t raised to the b minus 1 power dt. So how will we manipulate this now? So let's take a to be half, and b to also be half. So we have the beta of half comma half being equal to the integral from 0 to 1 of t to the half minus 1 is negative half times 1 minus t raised to half minus 1 is negative half dt. So we have the integral from 0 to infinity. Half power is basically a square root, and negative is basically reciprocal of that power. So we have dt over square root of t times square root of 1 minus t. So now how do we calculate this exactly? Looking at the form of the denominator, a trig substitution would be very useful here. So let t equals sine squared theta, so that when you take the root you only have a sine theta. So dt is naturally 2 times sine theta times the derivative of sine theta, which is cosine theta d theta, chain rule basically. So we have beta of half comma half now being equal to integral. So when t is 0, what value of sine will be 0? Sine squared will be 0, right? Sine of 0 is 0, so sine squared of 0 is 0. And when t is 1, what value of sine squared theta will be 1? If you take theta as pi over 2, you'll have 1 squared, which is 1. So upper bound is pi over 2. dt is, as I said, is 2 times sine theta times cosine theta d theta divided by square root of t is basically sine theta, right? Because t is sine squared theta, so sine theta, and 1 minus t is 1 minus sine squared theta, which is 1 minus sine squared theta. Let's write that as it is for now. Now in the denominator we have integral from 0 to pi over 2 of 2 times sine theta times cosine theta d theta divided by sine theta times 1 minus sine squared theta is cosine squared theta. The root of that is a cosine theta. Now notice that this cancels with this, cosine cancels with this cosine, and we are only left with 2 times integral from 0 to pi over 2 of d theta, and that is just going to be 2 times pi over 2 minus 0. So 2 times pi over 2 or pi. And what is all this equal to? The beta function of half comma half. So according to our computations, we obtained the beta function of half comma half to be nothing but pi. Fair enough. Well, how is that useful exactly? So there is another formula. Beta of a comma b, for example, is equal to gamma of a times the gamma of b divided by the gamma of a plus b. So if we have the beta of half comma half, this is gamma of half times the gamma of half divided by the gamma of half plus half. So this is nothing but gamma of half, but the whole thing squared, divided by the gamma of half plus half is 1, so gamma of 1. And now what's the gamma of 1? So now notice for positive integers we have this formula, n factorial is equal to the gamma of n plus 1. So for to obtain gamma of 1 we need n equals 0. So when we do that, we have 0 factorial equals the gamma of 1, and we know that the 0 factorial is 1. So finally we have beta of half comma half is nothing but gamma of half squared, because the denominator is just 1 now. But how does this relate to our Gaussian integral, you may ask? Well, let me remind you that the gamma function, say the gamma of n is equal to integral from 0 to infinity of e raised to negative x times x raised to n minus 1 dx. So to obtain gamma of half, we plug in n equals half, we get gamma of half equals integral from 0 to infinity of e raised to negative x raised to half minus 1 is negative half dx. Now we can write this as a square root, integral from 0 to infinity of e raised to negative x divided by square root of x dx. Well, but does this seem similar to something? Well, yes, because if you remember our original problem, we had exactly the same thing except we had a factor of 2. So to obtain that factor, we can multiply and divide by 2, so that we have 2 times integral from 0 to infinity. Let's change the variable because it's a definite integral, we can do that. Negative u divided by u du, we multiplied by 2, so we divide by 2. And now notice that this is just our substituted form of the Gaussian integral. So we have 2 times the Gaussian integral equaling a gamma of 1/2. And why do we want the gamma of 1/2? That's because of this beta formula, right? So beta of 1/2 comma 1/2 is basically gamma of 1/2 squared. We know the value of gamma of 1/2, so squaring that 4g squared. But what is our beta of 1/2 comma 1/2 equal to? We calculated that, we just computed that it's equal to pi. So all this, so basically 4g squared is all equal to pi. Pi equals 4g squared, g squared equals pi over 4, and g equals square root of pi over 2. And that makes sense because we have a half of the total of Gaussian integral. We only have the integral from 0 to infinity of e raised to negative x squared dx, instead of having negative infinity to infinity. In that case we would have pi because of symmetry. But since we have integral from 0 to infinity, this is square root of pi over 2. So that was using the beta function. And now it's time to actually use the gamma function independent of any other function. So now let's use Euler's reflection formula here. Euler's reflection formula. So what that says is, say if you have gamma of z times gamma of 1 minus z, that's equal to pi over sine of pi times z. So now if we plug in z equals half, give gamma of half times gamma of 1 minus half being equal to pi over sine of half pi. So we have gamma of half times 1 minus half is half, so gamma of half is equal to pi over sine of pi over 2. This will be gamma of half, but the whole thing squared, and pi over sine of pi over 2, if you know basic trigonometry, is 1. So gamma of half is just square root of pi. But what's gamma of half? Let me remind you, the gamma of say n is integral from 0 to infinity of e raised to negative x times x raised to n minus 1 dx. So if you now plug in half, gamma of half will be integral from 0 to infinity of e raised to negative x divided by square root of x dx. And how does that relate to our Gaussian integral? This is basically 2 times integral from 0 to infinity e raised to negative x divided by 2 root x dx. And now notice that this is the Gaussian integral. So we have 2 times the Gaussian integral. So now plugging this over here, we finally obtain 2 times the Gaussian integral is nothing but square root of pi. In other words, g is nothing but square root of pi over 2, and that makes sense because the integral from 0 to infinity e raised to negative x squared dx, and it's from 0 to infinity, not from negative infinity to infinity. In that case, we would obtain a square root of pi term. So these are the 2 ways of finding the Gaussian integral using the beta function and the gamma function. So I think this technique is probably the easiest, the fastest, and the most convenient considering other techniques. But still, to restate the conclusion, we have g equals integral from 0 to infinity of e raised to negative x squared dx. We used u substitution and converted it, and then basically took beta function and gamma function separately, and then came to a convenient gamma of 1/2 representation of this, and this is square root of pi over 2. And this, since this is symmetric about the y-axis, we have integral from negative infinity to positive infinity of e raised to negative x squared dx, and that's basically 2 times g because it's an even function. So that's 2 times square root of pi over 2, and that's square root of pi, which is approximately 1.707 recurring. Obviously it's pi is irrational. That's basically it for this video, guys. Please like, share and subscribe to my channel. Recommend me to your friends. I need to grow, guys. I want to make a huge YouTube community someday. So, and you can follow me on Instagram, gamma_digamma. I post math art and math related stuff. I'm going to develop that further. So until then, stay home, stay safe. Have a great day. Peace out.